Hello. So, hello everyone. Today we are here with a lecture video on all name reactions that are in your class 12 syllabus in one shot, organic chemistry, presented by Alpha. And I am Anurag Devnath, currently doing BTech third year in NIT Agartala, electrical engineering major. So, I'm going to teach you all the organic chemistry, like the name reactions mostly in this lecture. So without further delay, let's start. So before that, I want to give a brief or a gist of what we are going to study here today. So we have actually 6 chapters in organic chemistry. That is your haloalkane, haloarenes, that is alcohol, phenol, ether, your aldehyde, ketone, carboxylic acid, amines, nitrogen containing compounds, and your biomolecules. Sorry, it's 5. So name reactions are mostly in your first 4 chapters. There is no particular name reaction in your biomolecules. So we'll start with haloalkane, haloarene. It's a very important chapter. It's connect to all the rest chapters. That is your alcohol, phenol, ether, your aldehyde, ketone, carboxylic acids, and all. So let's start. Let's see what is our first name reaction. So this is our first reaction. That is your Finkelstein reaction. Very important reaction. What we do, haloalkane, haloarene chapter, we deal with all alkyl halide compound. So here alkyl iodides are often prepared by the reaction of alkyl chlorides. So bromide with NaI dry acetone. This is your reagent. See properly. Your sodium iodide and your dry acetone. Dry acetone here, it is your polar aprotic solvent. So basically polar aprotic solvent are those which does not give H plus or does not take H plus in their solution. So in exchange of that, you can use your DMF, or question may come DMF and sodium iodide. That means the same thing. So what we do here, you are given an alkyl halide that can be your chloride or bromide, anything. So you just react with your sodium iodide. So sodium iodide here, it's the nucleophile that we get here, that is I minus. This will attack this species. This is your attacking species. This will attack here, and your halide group will leave. Halide group here, chlorine is your halide, your bromine. So you want to change that. So also we know that this reaction follows SN2 mechanism. It's important to write here. SN2 mechanism. So this is your leaving group, your chlorine, bromine, and this is your attacking group, or the group which is attached to your alkyl group. So I can write here with an example, CH3. Suppose Cl you have, you want to react Finkelstein, NaI, dry acetone. So I'm not writing the whole thing here. So you get CH3I basically. So why this reaction? Why we have to like seriously react it with sodium iodide and your dry acetone? It's because this reaction, in this reaction, the product we get, that is your NaBr, in case you react it with CH3Br, your NaCl, which when you react it with CH3Cl. So these are the products. So what does product do? Product just settles down. Easy. It just precipitates out. Here written NaCl, NaBr thus formed in precipitated dry acetone. It facilitates the forward reaction according to Le-Chatelier's principle. So what actually happens, that the equilibrium is shifted to your product side. So what we need, we just need the product, nothing else. So just to increase the efficiency. So this reaction is very helpful for us. So this is our first reaction. Moving on, we have Schwarz reaction, very important reaction. In last reaction we have added iodine, and here we are going to add fluorine. So how do you do? Synthesis of alkyl fluorides, that is your CH3 F, your CH3 CH2 F. All these compounds is best accomplished by heating an alkyl chloride bromide in the presence of metallic fluoride, such as what are the reagents? Learn these reagents. AgF, Ag2F2, your cobalt fluoride, your SbF3. These are the reagents. So also I want to highlight one point, that is all the reactions that we are going to study is highly based on our NCERT. So this video will be your board proof, or also I am going to discuss some topics which are based on your entrance examinations, which are very much likely to come. So I'm going to discuss both, but also I will keep the video short as much as possible. So the reaction is comes as Schwarz reaction. It's up to some scientists or anything. So here is one example. Your CH3Br reacts with AgF. Here it can be your AgF2, your COF2. It does the same thing, only it adds fluorine. Khatam. AgBr is your byproduct in case here. So here is one example. Suppose CH3. Suppose here you are adding again CH3 group. You are having Br. So you react with suppose COF2. So what will be your product? What will be your product? Just write it in a copy. Then we can move on. Fluorine group is added. So this reaction also follows SN2 mechanism. So here attacking species is your this F minus is your nucleophile, I guess. F minus is your nucleophile. It attacks here and the bromine. So it's very easy, simple, and basic. Let me clear the board for you so you can have a clear look. See, this is the example. We have Senmeyer's reaction. Senmeyer's reaction. Before that, you have to learn what is diazonium or diazonium salt. So those who will be watching after completing the whole syllabus, they know this thing. What is diazonium? Replacement of diazonium group by iodine does not require the presence of cuprous halide. Whatever written is here. So you know the thing. So for those who don't know, let me tell you what is diazonium. Diazonium is nothing but when you react your aniline group. This comes from your chapter compound containing nitrogen. So when you react with your HNO2, your HCl at 273, 278, very interesting reaction, Kelvin. So you get diazonium salt. This is your diazonium salt. So this is the structure plus X minus. So it depends on X minus can be your Cl minus, X minus can be your bromine minus. If you're using HBr, then it will be Br minus. Whatever. Senmeyer reaction, nothing but here it is saying cuprous halide. Cuprous halide. Normally, what do you? Many reactions. Your there is one kind of Senmeyer reaction. There is one kind of Getterman reaction. So in your later chapter, so they said ki Cu I2 or whatever CUI is needed, just copper. It acts as a co-catalyst. But here, Sanmeyer said we don't need any co-catalyst, that is your cuprous halide. We don't need that. It is done simply by shaking the diazonium salt with potassium. Potassium iodide, here I minus is your nucleophile. I minus will exchange the group with this and I will be added in your benzene ring. Simple reaction and nitrogen gas will be evolved. Very simple reaction. Next, moving on, what do we have? Senmeyer's reaction here. As I've already discussed, how do you get your diazonium salt? This is your reaction NaNa2, HX. Here you can write HNO2. You can write HCl. You can write anything. This temperature, mentioning this temperature is mandatory. And here this is your product. See here, copper, so like this. We'll discuss the same thing in later part. So suppose Cl minus is there. So you react with your Cu2, Br2. Suppose so you get this. Br will be added to benzene. We'll discuss this later part. Next to Grignard reagent, very important thing. People, I will say this will be your confusing part. Student confuse a lot here because Grignard is something like this is what is attacking species. How can magnesium gets attached to bromine with the same alkyl group? Question may come, right? So most organic chloride, bromide, iodides react with certain metals to give compounds containing carbon metal bonds. Right? Such compounds are known as organometallic compounds. What are they? They are organometallic compounds. Why? Organo, this is the organic part, and metallic. Where is your metallic? Organic, organo part, and this is your metallic part. How this forms? Suppose see, if I have to break this, you can write here like this CH2. Suppose I'm just showing how does this compound exist. This is your Br minus, this is your Br plus. In total, this neutral, so it forms a it forms metallic bond, and this is your Grignard reagent you get. What is the reagent? Dry ether Mg. That's it. Dry ether Mg. I can give you example. Wait, I can give another example if you need. Also, if you have any doubt in any slide of this video, so you can just comment here, comment down below. So, suppose you have this a simple CH3Br. What is Grignard reaction? Nothing but Mg, magnesium metal, your dry ether. Just this is a compound CH3 Mg. Sorry. Okay. This is a compound. So here it is the same. There are many reactions I can. There are many examples I can show you, but I have to keep the video short. I have to tell you everything, all the name reactions in one video. So I'm moving on. So what do we have? Very interesting, very funny reaction. For me, it was very funny. Like, acha, let me discuss. Wood's reaction. What is Wood's reaction? Alkyl halides. We're dealing with haloalkane, haloarine. So alkyl halides react with sodium. What is the reagent? Sodium and your dry. That's it. Learn this. What is the reagent? I will give you short tricks. If you don't remember, if you can't remember everything related to organic chemistry, I will tell you how to remember. To give hydrocarbons containing double number of carbon atoms present in the halide. This reaction is known as Wurtz reaction. Very popular, very easy. So you are using reaction species. This is your CH3Br, methyl bromide. You react with 2 moles of methyl bromide. That is here user 1, this is your 1. So you react with sodium. So what does it happen? Either you are getting this ethane. How? Let's see. CH3Br. 2 species will needed to react. So here you are seeing 1 carbon. Just carbon number doubles. In Wurtz reaction, carbon number doubles. If you are reacting with ethyl something, so it will be double up to propane. If you are reacting with ethyl something, it will convert to propane. If you are reacting with 4 carbons, it will convert to your 8 carbon compound. That's it. It will double up. So what happens here? Sodium reacts. Sodium, what does it take? Sodium takes Br. So how everything happens? We know Na plus, Br minus, Br goes to Na. So it takes 2 bromine from 2 moles and just attaches this. Easy. Just attaches. So here is one example if you want CH3, CH2, Yeah. Let's see what will be the compound. What is our reagent? Na, dry ether, whatever. What do we get? We get propane. Also, we need 2 moles. I'm writing here. So this will develop. Sorry if my handwriting is bad. Sorry, I really apologize. I will correct it. Moving on, we are done with Wurtz. Very interesting, very funny reactions for me. So this is your fatigue. Fatigue is nothing but aryl halides, all those who are containing aromatic ring in them. Give analogous compounds when treated with sodium in dry ether. Same reagent is used in fatigue as well, in which 2 aryl groups are joined. Just 2 aryl groups are joined. This is your diphenyl. So you are reacting with phenyl. It takes suppose bromine. Suppose right here bromine. Here it can be chlorine also. You can do the same thing with chlorine. Same reaction, you will get diphenyl. Suppose. So bromine, dry ether, and you get 2 benzene ring attached to each other. This is the product. And here is one example. Same example. So here, this is your fatigue reaction. Okay. Now we'll go to one reaction that includes both the Wurtz and fatigue part. So let's see. If you want to write anything, you can write from it. Moving on, we have Wurtz fatigue reaction, nothing but 2 reactions combined to each other. We have discussed alkyl. I'm improving my handwriting for you. This is your aryl. Now, I will take one species from here, one species from here. So here I am using benzobromine. So here I am using methyl bromide. Same Na dry ether is your reagent. So what product do you get? You get your toluene, that is your Br minus comes out. This Br comes out. Then benzene is attached to your CH3. What is the common name? Common name is toluene. What is the IUPAC name? This is your methyl benzene. The same byproduct. You can do with different kind of I can give you like hundreds of examples for this. So I'm writing one example. Just suppose same I'm doing this. Br react with CH3 CH3, suppose Br. So what is the product? You know what is the product? This will be the product. CH3. How many groups? 2 groups. This is the product. So I'm going to keep the page clean, so you can just take any screenshot if you want, or if you want the PDF, you can just ask in the comment section. I guess it will be provided to you. Thank you. Next reaction is Friedel-Crafts alkylation. This reaction is very common in your first chapter, your second chapter, your third chapter, your alcohol phenol, your aldehyde ketone, and your this amine chapter as well. So Friedel-Crafts alkylation is an electrophilic aromatic substitution. It's an electrophilic aromatic substitution. So what we get electrophile from here. So this will be your electrophile. So you know electrophile, nucleophile. I'm not going to discuss this. For an alkyl group R plus, see here, R plus is introduced into an aromatic ring using an alkyl halide RX and a Lewis acid catalyst AlCl3. Same catalyst we'll be using in all the reactions, AlCl3, anhydrous AlCl3. Sorry. So this is your electrophile. What do you know? You know plus attracts minus. Okay. So though chlorine deactivates the ring, it creates resonance where we get minus charge here, here, and here. We all know this. This is your ortho position, this is your meta position, this is your para position. So when electrophile comes, then hydrogen will be replaced, that is your substitution. Then hydrogen, in case of hydrogen, will put here the electrophile, that is in case this is your CH3Cl. So suppose what will be the electrophile in this case, say. So break this is your electrophile. Very easy, just break the bond, give chlorine minus, give them plus. So this is your minor product, this is your major product. If I have to discuss from NCERT, then minor means like there are 2 bulky groups are present, so this will be your minor product. Major product will be this because it fits the crystal lattice perfectly. I guess this is your written in your NCERT, you already know this, why this is your major product. So CH3 group will be introduced either in ortho, we know this is para, or ortho or para position, because minus charge migrate from here, here. So, you know the resonance. So this is your IUPAC name. This is a Friedel-Crafts alkylation. Many examples can be given. You know when anhydrous AlCl3, your CH3X, CH3Br, or CH3Cl, anything is given like alkyl halide, any kind of alkyl halide, you just go for Friedel-Crafts alkylation. What is acylation? Acylation is nothing but here the species is this acyl chloride. We call it acyl chloride. So Friedel-Crafts acylation is an same reaction or an acyl group. This is your acyl group. What is your acyl group? Any alkyl group will be there. C double bond O carbonyl group will be present, and your this is your acyl chloride and this is your acyl group. What charge does it take? See here, CO minus. So if you break this, it retains a plus charge. It's minus. The same thing happens. It's an electrophile. This is your electrophile. This is your electrophile. So is introduced in an aromatic ring. So this is the electrophile CH3, C double bond O. This bond will come over here, either here or here. So here you can see 2 bulky groups. Same. This will be your minor product. This will be your major product. That's it. Sorry. I guess one reaction is skipped here. I will see which reaction. By the way, moving on, we have Kolb's reaction. Another important reaction, phenoxide ion. We know benzene ring, sorry, phenoxide. Sorry. So we know that phenoxide ion, that is your more reactive than your normal benzene ring. So phenoxide ion is generated by treating phenol with sodium hydroxide. See, sodium hydroxide is react with phenol to obtain phenoxide ion, that is your O minus Na plus. This is more reactive, very much reactive than this species. So what it does, reactive with phenol towards electrophilic aromatic substitution. Hence it undergoes electrophilic substitution with a carbon dioxide. Air, okay, carbon dioxide is a electrophile also. Electrifying doesn't necessarily mean you should have plus charge, not that. If you have vacant orbital, you can be an electrophile. With carbon dioxide, a weak electrophile, orthohydroxybenzoic acid is formed as the main reaction product. Don't go into that big name, that is your salicylic acid. This is your salicylic acid. See this. So what does it do? In simple words, you have phenol. You have one step here, you have one step here. Then what is the main product? This is the main product. This is the Kolb's reaction. In between, you react with CO2. In between, you react it with NaOH to obtain the phenoxide ion. So two parties required. That is your reaction with CO2, carbon dioxide gas, and you react with phenoxide. Sorry, sodium hydroxide. So sodium salicylate. So what you have to actually do, that is you have to do hydrolysis. If you do hydrolysis, then only you can obtain COOH group. Either Na or a metal will be attached to it. So this is your hydrolysis. You can write here for understanding. H plus H3O plus water, anything is written, that means hydrolysis. You have to like remove this group and add H plus. So one step, two step, three step. So this is your Kolb's reaction. Important from your first chapter. Next comes very important reaction, very common reaction, very important one. Wait. So on treating phenol, what we know, same language. Also, this PDF has been made from majorly from your NCERT. I have taken things from NCERT. I have taken language, your theory from NCERT, and other online. I have gone online resources. So on treating phenol with chloroform, that is your CHCl3, in the presence of sodium hydroxide NaOH, CHO group is introduced at ortho position. We know everything of benzene ring. This reaction is known as Dimertimon reaction. Very popular, very familiar. This is a very easy reaction. I will say this is a easy asked. Many a times this reaction is asked, though it is very easy, very common. So that's it. So I can show, in next slide you have the reaction. So let's see. So this is your phenol. You react with chloroform, aqueous NaOH. You get phenoxide ion here. CHCl2 group is introduced here. This is your intermediate. Many a times, you know, CBSE is making the question making has been changed from my times. In my time, there used to be a lot of direct questions, but not anymore. CBSE asking from anywhere. They are making questions out of answers, answer out of questions. So you have to learn the intermediate. There is no other option. You have to learn the intermediate. So this is your intermediate, know this, and after reacting with the sodium hydroxide, CHO group is introduced here, and this remains the same. There is a phenoxide, and this is your hydrolysis. Simple, phenoxide transform into OH and your CHO group. This is a salicylaldehyde. One is salicylic acid, one is salicylaldehyde. Remember this name. I have seen board question paper. They kind of like ask not IUPAC name, they use common names like salicylaldehyde, salicylic, glycolic acid, whatever is there. So you have to remember all the things. This is your salicylaldehyde. So we are done with Dimertimon. Moving on, what do we have? This is not a name reaction. While making this whole PDF presentation, I thought I must include these two things. That is your normal phenol reaction with zinc dust, and your oxidation reaction. So phenol converted to benzene ring on heating with zinc dust. With zinc, what does it do? It just takes the oxygen. So conversion, while doing conversion, you can see this minute reaction. So oxidation, what we have? Oxidation of phenol with chromic acid, that is your Na2Cr2O7. This is your chromic. This is your chromic acid. A conjugate diketone known as benzoquinone is formed. Diketone, like two ketone group will be present over here after reaction. So these are heavily oxidizing agent. Heavily oxidizing agent, heavily oxidizing agent. You are oxidizing the whole thing. Phenol group is converted to your benzoquinone. So two ketone group will be introduced here. This is not name reaction, but I thought it may be important for you, so I'm letting you know. So next is William ether synthesis. Very important. And what do I say? William ether synthesis, people mistake a lot here. People do a lot of mistake. So just see. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ether. Both we can do symmetrical ether, that is your this is your unsymmetrical ether, that is your symmetrical ether. See, this is your symmetrical ether. So you can do all this. So here, see, here alkyl group is present in this method, and alkyl halide is allowed to react with sodium alkoxide. Two things we need, that is your alkyl halide, is your CH3Br. So I'm going to give you important points regarding this. People do a lot of mistake. Why, when, how? I'm showing you. Wait. The second thing you need alkoxide ion, that is your NER group that contains your O minus NF or RON. I have a tendency to write plus minus, so I've been doing this from my age for better understanding. So let's see. Here what we get, you get basically ether. This group will attach to this group, and these two will be attached to each other. NaX. So here is one example I am showing here. I'm not writing anything. So see this example. You are using alkoxide ion. Here it is your tertiary butyl group, and your T-butyl, you can write here T-butyl, common name, T-butyl, whatever. So it reacts with your methyl bromide. What does it do? O minus, this lone pair comes to CH3, and this bond breaks. Bromine takes what? Minus charge. CH3 gets plus charge. This minus charge gets attached to plus charge, and this is your final product. Easy. This is your byproduct. You don't need to know the byproduct. So one thing I was going to share here was alkyl halide. Make sure while doing Williamson ether synthesis, your alkyl halide must be 1 degree. Must be. It can be 2 degree, it can be 3 degree, but what effect will do when it gets the alkyl halide is 3 degree? We'll see this. Your alkyl halide must be of 1 degree, and your alkoxide ion must be of 2 or 3 degree. Must be of 2 degree, 3 degree carbon alkyl group, or this can be 1 degree also. When you react with 1 degree alkyl halide with 1 degree alkoxide ion, the same William ether synthesis will follow up. But when you react, when you just go alkyl halide, if you are using this alkyl halide, suppose I'm not writing the hydrogen, so this is 3 degree. If you are going for this, you are taking the alkyl halide 3 degree, and your alkoxide, suppose 2 degree or 1 degree, suppose ONA. Suppose here 1 degree you are taking. So this reaction will not end up forming ether. It will end up giving you an elimination product, that is your alkene. Reaction will take place, definitely. This reaction will take place where? This is a separate part. This ethers containing substituted alkyl groups, secondary, tertiary, may also be prepared by this method. This reaction involves SN2 atom related to this of an alkoxide ion on primary alkyl halide, whatever. So I was saying ki here, if you take the alkyl halide 3 degree and the alkoxide ion 1 degree, then what do? You will get a double bond. Elimination will happen. So why? I know those who have read NCERT, they know why, but I will discuss it. Don't worry. So here are a few examples for Williamson ether synthesis. So Williamson ether synthesis becomes elimination or your right alkene. When just you convert the alkyl halide, if you take the alkyl halide 3 degree alkyl halide, or you keep the alkoxide ion 2 degree or 1 degree, it becomes an elimination reaction basically. See here, language is written here, you can understand. Also see the example first, then after I am coming to the theory part. So what do you have? This is your example here, ethyl iodide react with sodium alkoxide. See, here 2 carbon, here 2 carbon, then ether will be your symmetrical, definitely. So this is your product. So here you can see it is 1 degree, and this is your 1 degree alkoxide. So here you can see the alkoxide ion is 3 degree and the alkyl halide is 1 degree. Here you can see it is benzylic, very much stable. You have to go for the much stability. You have to give alkoxide more stability than the alkyl group. So here, this is your 1 degree. A few examples. This is your product. So what happens? Better results are obtained if the alkyl halide is primary, as I have said earlier. In case of secondary, tertiary, elimination competes over substitution. So many products are formed. Okay, that doesn't mean the reaction to this not there. Reaction. In some cases, you get 30% X, 50% suppose Y, and your rest is Z. Okay, rest percentage. So what we consider as the product, we consider those species yield. So in that order, we follow organic reaction. So here the major product will be your elimination reaction. It will form an alkene, and your minor product will be your ether when you react with 3 degree and 1 degree. But if you keep this 1 degree, 1 degree, 1 degree, 3 degree, 1 degree benzylic, or 1 degree, 2 degree, you will get your Williamson ether synthesis. No problem. You will get ether. This is, you are getting ether. This you are getting ether. This you are getting. No problem. But when you go for like here, as I've said, this, then you will be the major product. Alkene will be the major product. Elimination reaction will compete. It's a very important thing to note down. So if you want example, I can give here. Suppose you are taking this. This is your alkoxide ion species. You're reacting with 3 degree. If you want 3 degree, okay. What will be its product? Its products will be. See what happens. Suppose 2 degree you're taking. This will be your major product. Instead of getting ether, you will get an elimination product. This is your alkene. So moving on, we have Dawes process, simple process used for formation of phenol from chlorobenzene. You have to not do any H, nu, Cl. You don't have to add Cl from here and there, whatever you are doing. Chlorobenzene you get. So NaOH at high temperature, at high pressure, it's a phenoxide ion, and you react with HCl and H comes over here. Simple. So this is your Dawes process. So in many conversion, you may need this. I was saying this. How do you get chlorobenzene from? Basic one. So you need Gauss-Prussian conversion. Next, moving on, we have Scott and Bauman reaction. Just see this, I am covering. So Scott and Bauman reaction, it is a kind of your alkylation, you can say your alkylation, acylation, it kind of your Friedel-Crafts reaction. What is say? When applied to phenol, involves the acylation of the phenol with an acyl chloride in the presence of base, typically NOH, pyridine, to form phenyl ester. This reaction is nucleophilic acyl substitution, where the phenol in its deprotonated phenoxide form acts as the nucleophile. So what acts as a nucleophile? Deprotonated phenoxide form. I'm not going into the mechanism because the lecture will become like 3-4 hours, so I'm not going to the mechanism. Just see here, this is your phenol group, this is your acyl group. Cl leaves, it obtains plus charge, O minus, then plus will attract minus, and this compound will be formed. Okay, this is your phenyl benzoate. So Scott and Bauman is done. Moving on, we have Friedel-Crafts reaction. Same as I've said, you will get these things in your. We have done these things in your haloalkane, halourine. We are going to do the same thing in alcohol phenol ether. So this is your alkyl acyl groups are introduced to orthopara position reaction in the presence of anhydrous aluminum chloride, Lewis acid, that is your catalyst, and OCH3 is present here. OCH3, this is your CH3Cl. CH3Cl, we get nucleophile CH3 plus. So this comes of ortho position, this comes over meta position. Sorry, para position. So this is your minor product, this is your major product. And one thing from this, you can write in your copy, that is your OCH3 group is OP directing. You can write in this copy, because in conversion you may have doubt how to add the nucleophile. So in case of OCH3 is present in benzene ring, so you have, it will be in O and P position. So here it is given. So here is one example again. This is your acylation, COCl. Acyl group is present. This was your alkylation. So CH3 COCl, your plus, your OCH3. It will come over here. It will come over here. Ortho and para position. This will be the product. OCH3 is present. From acyl chloride, what we are getting? We are getting CH3CO. Easy. This will be the minor product. Major product, you know, P position, para position. This is your Friedel-Crafts reaction. Moving on, we have nitration. Very basic. Anisole reacts with. This is your anisole. Common name is anisole. Mixture of concentrated sulfuric acid and nitric acid to yield a mixture of orthopara nitroanisole. This suppose major means what? Major means 55%. This means 45%. In that sense, we are saying minor major. So when you react with it with H2SO4 HNO3, the concentrated sulfuric acid, you get NO2 group attached to the benzene ring at ortho position as well as para position. The nitration done. Next is Stephen reaction. Stephen reaction is very important. Stephen reaction, we are converting the nitrile group to your aldehydic group. So this chapter is named aldehyde ketone carboxylic acid. So whatever name reactions we are seeing, that's mainly to convert whatever species is given to your aldehyde. So we'll come to the later part, the ketone and carboxylic acid. So this is the language. In organic chemistry, used to prepare aldehyde from nitriles. This is your nitrile. Suppose, so here R is given for reference. Suppose CH3, CH2, CN. What are the reagent? Learn this. SnCl2 stannous chloride. Your HCl is your reagent. When you react it with both, you get a, I can write in one step also. So this is your amine group is attached first, NH group is attached, and then after hydrolysis, CHO group is introduced here. So, you can see. So I can show the mechanism, but it will take time. This will be break, and this will be OH will come here. NH3 will be NH3 will be. So RCHO group is introduced. So if I write directly H3O plus here, so you can get CH3, this C double bond O H. CN group, sorry, 2 number का. Double bond O H. That's it. This is the product. So I guess you understood. Moving on, what we have etard reaction. Etard is also to prepare benzaldehyde from benzene, I guess. Chromyl chloride oxidizes methyl group to chromium complex. This is your chromium complex, and yes, you have to know the whole thing. You have to learn the thing. What group is attached here? OCRO HCl2 whole bracket 2. Which on hydrolysis gives corresponding benzaldehyde? One, you react it with chromyl chloride. This is your chromyl chloride, and carbon disulfide is your solvent. It gives this complex, and after hydrolysis, you will get benzaldehyde. A CHO group will be introduced into your benzene ring. So, I guess you understood etard reaction. Yeah, toluene, common name is toluene, benzaldehyde. So, this is your reagent. CrO2, I am writing here again, CrO2, Cl2, and your CS2. This is your chromyl chloride. Next, Getterman-Koch reaction. There are two reactions mainly, that is Getterman. One is Getterman. What is Getterman? Aldehyde synthesis, normal Getterman. One is Getterman-Koch reaction. So what is why it is Koch reaction? What is difference? Let's see. Synthesization of an aldehyde from an aromatic hydrocarbon. Aromatic ring is present. Carbon monoxide, hydrogen chloride, catalyst containing aluminum chloride is Getterman-Koch reaction. This reagent is Getterman-Koch. That's it. What do? You just convert normal benzene to your benzaldehyde. CHO group is introduced. Additionally, learn this. The reagent, what are they? Carbon monoxide, 1. Your second number is HCl. Third number is anhydrous AlCl3, Lewis acid. And fourth number is copper. Why copper? For not unable to see, I am reading it for you. The Getterman-Koch reaction is not applicable to phenol or other phenol ether substrates. If zinc chloride is used as a catalyst in the Getterman-Koch reaction, traces of copper chloride is often necessary since it acts as a co-catalyst. See, traces, if you just need trace amount, here also ZnCl2 you can write, ZnCl2 is used. So you Getterman-Koch reaction not applicable to phenol. You can't do this with phenol. You can't put Getterman reagent here, CO and your extra things, and you will get benzaldehyde. No, it will not react. And ether substrate means this, any ether substrate, any sol, it will not react with any sol. That's it. So if zinc chloride is used as a catalyst in the Getterman-Koch reaction, so if you have zinc chloride in case of AlCl3, so CuCl is also needed in trace amount because it acts as a co-catalyst when you react it with zinc chloride. So I guess you understood. You can write. Moving on, what do we have? Getterman aldehyde synthesis, as I've said earlier, you can go through the language. Aromatic compound with hydrogen cyanide and hydrogen chloride, these are your reagent, HC and HCl. HC and HCl are your reagent in the presence of same AlCl3. This process type of electrophilic aromatic substitution similar to Fidelcraft reaction but specifically introduces an aldehydic group, CHO, in the aromatic ring. So this is your Getterman normal aldehyde synthesis. So HCN is your reagent. I'm differentiating it for you because I know students make a lot of confusion and mistake out of. This is your coach. This is your normal Getterman. What do I learn here? Tell me, what reagents were you using last time? First one is sorry, I guess it was a mistake. Sorry, CO. Second one was your HCl. Third one was your anhydrous AlCl3. I am focusing on the reagent because that's what you need for the reaction. That's why this video is not just organ name reaction, it's also about the reagents. Precisely, learn this. Anhydrous AlCl3, if you are using ZnCl2, you have to use CuCl in trace amount as co-catalyst. I'm writing here co-catalyst. Know the whole thing. Why, which reagent are you, why we are using this, only this reagent, why we are going by this process, you have to know this. Don't need to mug up everything, okay? Getterman, normal Getterman, what we have, HCN, we have react with your HCN, hydrogen cyanide. This your HCl is common in both, and again use your anhydrous AlCl3. Anhydrous AlCl3. So after that, as I've said, ki NH3 will come out from here. If I have to show the mechanism, so in that way. Whatever. Not complicate the thing. So this will be your product after this step. So you are doing hydrolysis, you are getting this benzaldehyde. OCHO group is introduced into your benzene ring. So then we go for hydrolysis here. H2O plus means what I have said earlier, hydrolysis. So I guess it's very clear to you. Moving on, we have very popular reaction, Rosenman reaction. Every name reaction is popular because I'm saying this, I have seen the question paper of your board examination and your all the question papers I've gone through and your entrance exam also. What they do in entrance exam, I know NEET is completely based on your NCRT. I've noticed one thing that they give similar reagents. So it's not name reaction. It's like normal. I'm talking about organic chemistry. Organic chemistry, okay. Organic chemistry, they just change the reagents. They give you similar looking reagents. You have to find out what will be your electrophile, nucleophile, what will be your attacking species, and after that you can solve any question from your organic chemistry. For NEET, I'm talking about NEET and your JEE for your entrance. And let's not go in that part. We're discussing Rosenman reduction. It's a reduction reaction. A reduction is nothing but hydrogen will be introduced. Where acid chlorides converted to your aldehyde using hydrogen gas over a palladium catalyst supported by barium sulfate. So why palladium, why barium sulfate, why hydrogen? Let me discuss. This reaction is selectively reduce acyl chloride to aldehyde. So selectively means HCl will get out, hydrogen will be introduced. Okay. This reaction is catalyzed by palladium. What are the catalysts? Hydrogen gas, palladium, barium sulfate. And why barium sulfate? Barium sulfate act as a poison and reducing the activity of palladium catalyst to prevent over reduction to an aldehyde to an alcohol. So what is over reduction? Let me tell you. So why Rosenman? What is the purpose of BaSO4? So if you go, okay, here. If you don't use, suppose you are cutting down BaSO4, this H2 and PD, I guess you have known ki while reducing we have first reagents that we come through, that is the H2, PT, PT, Ni, nickel. I know, I guess you know all these things. So PD hydrogen, what does it do? It goes for continuous reduction, that is your over reduction. Okay, it will reduce here. What it will do, it will add hydrogen here one and here one, so it will finally you will get CH2OH. You don't want alcohol, you basically want benzaldehyde, your aldehyde group. So to avoid this part, we are using BaSO4. It's excess poison, it just restricts the reaction up to this thing only. No further reduction, no over reduction, nothing. So Cl will come out and H will be introduced. See here, I guess it's clear. So while studying, I guess many of you don't know why these things are you. What is the purpose? How does BaSO4 acts? Matlab why we are using barium sulfate on PD, and why? How come the reaction, and what is the mechanism? So I will try to tell you each and every single thing. So keep memorizing. Let's not discuss this part. It's very subjective. Entrance and your board examination. I was just saying entrance because nowadays CBSE is making many changes to their question set, question paper. They are like, as I said, they are making questions out of answers, answer out of questions, so you never know. Moving on, we have Friedel-Crafts acylation reaction. That we have already discussed. So wait a minute. What is written here? When benzene or substituted benzene is treated with an acid chloride, same COCl group, presence of anhydrous AlCl3 Lewis acid affords corresponding ketone. This reaction is known as Friedel-Crafts acylation reaction. Like you all know, this is the product of basic acylation. So we know this is a ketone, so that's what they are saying this. We have Clemmensen reduction. Next, we have Clemmensen reduction is from aldehyde ketone carboxylic acid. We are stuck to this one chapter already. Your aldehyde ketone carboxylic acid is a huge chapter. Students make a lot of mistake in this chapter. Students take a lot of confusion in this chapter. What happens, how happens, why happens. So we have discussed what Clemmensen reduction. Clemmensen reduction, I guess, is nothing but it will change carbonyl group of aldehyde ketone is reduced to your CH2 group. Carbonyl group will be completely reduced. So we know reagents which just reduce this to this. There are reagents. What are these reagents? Please write in the comment section what are these reagents. That your carbonyl group, maybe it can be your ethyl group, maybe it can be your ketone. Write this in your comment section. What is the answer? Maybe you are given ketone or your aldehyde. Here we are seeing it's directly converting CO to CH2. That means you are adding 2 hydrogen here, you are adding 2 hydrogen here, definitely. So what reagents are used to add 1 hydrogen? That is for your ketone and aldehyde both. You are to react with CO carbonyl group, you have to add 1 hydrogen here, 1 hydrogen here. You are adding 4 hydrogens. Here you are adding 2 hydrogens. So what were the reagents? It was in your first chapter, I guess, or in this chapter also. So what reagents we were using to add just 1 hydrogen? Write it in the comment section. And your other reagents are there. Already told you. So not go to that part. Discuss Clemmensen reduction. Carbonyl group, CO group is directly converted to your CH2 group. Whether it would be your ketone or aldehyde, doesn't matter. Treated with zinc amalgam. This is your reagent. Concentrated HCl, zinc amalgam, ZnHg, CONC, HCl. These are your reagents in your Clemmensen reduction. This reaction is particularly useful for reducing alkyl ketones, which are ketones with both of aromatic ring and an alkyl group attached to the carbonyl. So aromatic, it can be react with aromatic ring as well. These are two examples. I can zoom you. You can see the example. So this is your CH3 COCH3 ketone, and this is your reagent using, you are giving heat as well. So 4 moles of hydrogen will be introduced, 2 will go to oxygen, that will form water, and 2 will go to carbon. Okay, this is your propane. This is your acetophenone benzene ring. Same, you are using 4 moles zinc amalgam concentrated HCl. So CO group is converted to your CH2 group. The reagent. Done Clemmensen reduction. Moving on, we have your Wolff-Kishner, again very popular reaction. Many steps are there. So, sorry. So, a carbonyl group of aldehyde ketone is reduced to CH2 group, same treated with hydrogen. What is your hydrogen? NH2 is your hydrogen, followed by heating with sodium potassium hydroxide in high boiling solvents such as ethylene glycol. So, first part is your hydrogen. Second part is your ethylene glycol and your NaOH base. It can be NaOH, it can be KOH, it can be anything. What else you are going to do? You are going to do heat and ethylene glycol. So first it converts to an hydrazone, a compound. I can show you why. So I can give you an example. So, this is your complex. See here, suppose CH3. See, CH3 is there. So react with NH2, CH3. Double bond will go to here, right? Nitrogen. H2 will come out. NH2, and this is CH3. I guess you understand. And see here, after reacting it with base, strong base, ethylene glycol, same strong base, and giving heat, hydrogen will be introduced here. So, and nitrogen gas will be evolved. And this is the reaction. Same, C carbonyl group is changed to CH2. What is the reagent? What is the reagent? Hydrazine is your reagent. KOH is your reagent. First step, hydrazine. Second step, KOH, ethylene glycol, and heat. So you'll directly get this. No need to learn the hydrazone thing because it's an intermediate. I guess here it is shown the hydrazone same. In every reaction of Wolff-Kishner, hydrazone is produced. It can come to your MCQ question to ask what is the intermediate of Wolff-Kishner reaction. You have to write hydrazone. Hydrazone is nothing but double bond O vanishes and double bond N is introduced to your carbonyl group. Here a different example you can go through. So if you want me to like zoom and show you. here CO will get changed to CH2. As I've said, 80% is the yield. That's why it's the major product. There are other product as well. So here are a few examples. Acetaldehyde, acetone. You are reacting with acetone. Ethyl phenyl ketone, ethyl group, phenyl group. This is your IUPAC name, ethyl phenyl ketone. Reacting with Wolff-Fishner reaction, you get your CH2 group is introduced here, and your nitrogen gas. Same. Moving on. We have aldol condensation, very important. Theme, very important. What do I say? Very important reaction for all the board students and your all those who are appearing entrance. Aldehyde ketones having at least one alpha hydrogen. Alpha hydrogen is mandatory. Alpha hydrogen is mandatory here. Undergo a reaction in the presence of dilute alkali. What is dilute alkali? Dilute alkali, it can be your dilute KOH. It can be your dilute NaOH. If these two things are written in your reaction, just go for aldol condensation. Aldol condensation is also a two-part reaction. One is aldol formation, another is condensation. We'll go through. So it forms a beta hydroxyaldehyde. What is beta hydroxyaldehyde and why it is named beta hydroxyaldehyde? Beta hydroxyaldehyde is also known as aldol. Similarly, beta hydroxy ketones are called ketones. So respectively, this is known as aldol condensation. So I'm showing you in one step just to make you clear. Okay, this is not the actual mechanism, but I'm showing you for your, if you like, you can do any aldol condensation reaction with this thing. Just learn this, what I'm doing. In physics as well as in chemistry, you learn key that plus attracts minus. That's it. Minus attract plus. That's it. This is your organic chemistry, nothing but organic chemistry. Those students who say ki organic chemistry is very tough, I can't do organic chemistry, there is a lot of, you have to like mug up this reaction, that reaction. Not necessarily. If you know how to break things, if you know how to break the reagent, what electrophile you get, what nucleophile you get, whatever you get, you just need to attach the plus to your minus, minus to your plus. That's it. That will be your product. Okay. So let's not delay. I'm giving you with this example. This is for those students who don't know what is aldol condensation. If you know, this is actually one shot video. If you know the reaction, you can skip this part and later on you can watch this. You need 2 moles. You need to draw 2 ethanol. Let's see. Expose 1 carbonyl group. You need alpha hydrogen, right? Alpha hydrogen here, is it present? So what is alpha hydrogen? This is a functional group. Next carbon, it is called alpha carbon. Hydrogen attached to it is called alpha hydrogen. So hydrogen, take 1 hydrogen. We just need 1 hydrogen. Keep the same end as it is. This is alpha hydrogen. So what do? Break the bond. Oxygen is electronegative, minus. Carbon gets plus. Hydrogen, highly electropositive, highly electronegative, plus electron. It will come out as H plus. It will get minus. Plus attracts minus, minus attracts plus. That's it. Whole condensation is reaction is done. So I can draw here the product. This is your aldol. CH3, C, oxygen goes here, sorry, hydrogen goes here. Plus is attached to minus. Hydrogen remains as it is. Sorry for my bad handwriting. So CH2. This is CH2. I'm not used to doing like teaching on board. This is my first time. So please take it as it is. So this is your product. Okay. This is your, I guess this is your product. Okay. And then why beta hydroxy butanol aldol? Oh, beta hydroxy, why? See, this is your functional group. This is your alpha. This is your beta. Hydroxy group is present at beta position. That's why beta hydroxy aldehyde. It's called an aldol. So this is your beta carbon. That's why beta hydroxyaldehyde is named as such is. So next part, is your condensation. Okay, condensation is nothing but you take out the water molecule. Complete, easy. OH, H. That's it. Just need to heat, provide heat here. You can write here minus H2O if you want, up to you. So just take out the OH from one carbon and hydrogen from another carbon. See, everything remains as it is, CH. Double bond is introduced, sorry. I'm very sorry. Again, I am apologizing for my very bad handwriting. This is your product, I guess. Same product here. So this is for those students who actually have doubt or didn't understand angular condensation. After that, I am sure that you are not going to have any doubt. I guess it's clear. You have to just you have to break the bond from here to oxygen, give minus to oxygen, give plus to this carbon. Oxygen attracts hydrogen, give plus charge to your hydrogen and minus charge to your carbon, and plus attract to your minus. Same. So that's it. I'm done with aldol condensation. Moving on. There are two types of aldol condensation: crossed aldol and self aldol. Cross aldol, I know you don't like cross aldol because there are a lot of products are formed. There are a total of 4 products in cross aldol. Okay, why, when, how? Let me show you. And self aldol, we have already studied self aldol. This is an example of your this cross aldol reaction. Actually, here one carbon lacks alpha hydrogen, another carbon has alpha hydrogen. So that way this reaction goes. So you can see the cross aldol. There are two types of cross aldol in which both species have alpha hydrogen. Here you get 4 products, and in case one has alpha hydrogen and other does not, it will give you one product only. It's going to give you one product. So here in cross aldol, I am actually discussing about 2 species which both have alpha hydrogen. We are going to discuss in later slide. This is your reaction in one species. One species have alpha hydrogen. You can write down the examples here. This may come in your board exam or your entrance. So in cross aldol, where both the species have alpha hydrogen, let's see what happens. So there are total, I'm going to discuss this. So I can give you different example. Do this in your copy: CH3, CH2, CHO, dilute KOH. Do the aldol condensation here. 2 moles you need. Do it in your copy. Moving on, there is one theory part you can go through. And also, if you want the PDF, let me tell you again, if you want the PDF, you can ask it in the comment section. So it will be provided to you. The link will be provided. The PDF consists of, I guess, 60 pages, and it contains all the name reactions in one shot, one slide. So total of 65 pages are there. You can go through them. So it's also NCERT trusted. And let me tell you again and again, I have gone through the whole NCERT book, your part 2, to collect all the informations, whatever is given. You have done this. This is your cross aldol. I'm not going to show you the 4 reaction. Just know that 2 species are given here. That is your 1CH3 C double bond O H. Another one is your CH3 CH2 C double bond O. unmatched. Okay. Does it contain alpha hydrogen? Yes, it does. Does it contain? Yes. So 2 alpha hydrogens, 4 products. In one case, this will act as nucleophile. This will act as electrophile. Both. In this case, this will act as nucleophile. This will act as electrophile. In third step, this will act as electrophile. This will act as nucleophile. And the fourth step, this will act as nucleophile. This will act as electrophile. So here you can see here A, B is, they have denoted this as B, they have denoted this as A. A being nucleophile, electrophile to itself, this is the product. Let me I guess it is clear. So this is your A being nucleophile electrophile to itself, B being nucleophile electrophile to itself. This is your A being your nucleophile and B being your electrophile. This is your product. This is your fourth product. This is your first product. This is your second product. This is your third product. This is your fourth product. Anyway, is true. So I see what is written in here. Each aldehyde has an hydrogen and therefore can be converted into an into enolate to react with the carbonyl form itself with other molecules. So you can react it with both itself with another different molecule. So I've done this part. You can do the aldol condensation. This will be their product. If you do condensation, then OH will be reduced. OH will be water will come out. Then double bond will be introduced. Here one double bond will be introduced. Sorry. Go through the language. Next is your different product. These are from NCERT. You can do it at your home. You can not going to show you the whole thing. You on this access nucleophile, this access electrophile, and this is access electrophile, this access nucleophile. Moving on, we have simple or self aldol, cross aldol. These are products. This will be the product when you do this. Okay, this will be the product. Can you see this properly? I guess yes. If you have any problem, I'm writing the product here. Check out. This is your condensation. Complete. Moving on. We have Cannizzaro. Again, one important reaction, very much important. Know these two things. Just know in Cannizzaro reaction, you just need to know two things. One is one compound, of course, no alpha hydrogen. No alpha hydrogen. One thing, product will be your alcohol. and another will be carboxylate ion salt. Okay? Aldehyde which do not have alpha hydrogen undergo self oxidation reduction, disproportionation reaction actually. This is your oxidation, this is your reduction. This is your oxidation, this is reduction, reacting on heating with concentrated alkyl. What is the reagent in Kenizaro? Write in your copy. These are the reagents. One molecule of aldehyde is reduced to alcohol. As I've said, this is a reduced product. Understand the logic behind organic chemistry. Trust me, organic chemistry is very fun, easy to understand. It's not about mugging up the reactions, not about learning how this happens, what is the product. It's very fun to do. This is your oxidized product. Okay, so one example: formaldehyde. It does not contain any alpha hydrogen. It reacts with two species. We will use two species. One will be converted to alcohol, another one will be carboxylate acid salt. That is your, instead of O, hydrogen is introduced here. So you get methanol, your alcohol, and another is introduced. Hydrogen comes out, OK is introduced. The potassium formate. Why potassium? Because KOH is introduced. If you were to use, if you put NaOH concentrated, then it will be here N. Easy, simple. And keeping the board clean, you don't get. Here in case benzaldehyde, benzening, so Kenizaro can do both for benzening, both react to its alkyl halide, alkanes and both aryl compounds. It reacts with both. So benzaldehyde reacts with concentrated NaOH, it gives alcohol, and your sodium benzoate, carboxylate ion salt. Moving on, we have cross Kenizaro reaction. Important, you can look after. This can come in your exam. So here both the species will not have any alpha hydrogen. Both species will lack alpha hydrogen. Then one species will be oxidized. One species will be reduced. This will get reduced, this will get oxidized. Also a bunch of byproducts are formed here. I guess 4 or total of 4 byproducts are formed here actually. This reaction is not that much of efficiency. So in cross Kenizaro, what is the reagent? Same. Concentrated, as I've discussed, same reagent is used. Concentrated NaOH, concentrated KOH. Concentrated, I mean 30 to 33% concentration. They can give you 33% NaOH, which means concentrated NaOH. They can change it. So here you can see. So here, one example, same example, benzaldehyde. Then your formaldehyde, benzaldehyde converted to your alcohol, formaldehyde to your carboxylate ion salt. So here anisole is present, here P-anisyldehyde is present. So CHO group is present here. Then CHO group, OCH2 will remain as it is. This reaction, see this reaction. I'm writing here. OCH3. Nothing will happen to OCH3. OCH3 will be intact. This CHO group this is your formaldehyde, same concentrated NaOH, CHO will be converted to your alcohol. No effect on OCH3 and your HCOONA, carboxylate ion salt. OCH3 will remain as it is. It will just react with CHO group. I guess you understood. Moving on, we have electrophilic substitution reactions. Electrophilic substitution, nothing but this is your, see, according to this is ortho, this is meta, this is para. So while doing nitration, we have seen NO2 group is introduced where? At the meta position. From that we know, write it in your copy, CHO group is what directing? Meta directing. It will direct the group to meta position. Aromatic aldehyde ketone undergo electrophilic substitution at the ring in which the carbonyl group acts as deactivating and meta directing. Or definitely you have to know carbonyl groups is a deactivating group. Carbonyl group, your this fluorine, fluorine, bromine, iodine, whatever halide, you know, this all are your deactivating group. It deactivates the group. So here it will be introduced. HNO3 H2SO4 is your reagent, nitration. Next example is Hell-Bullard-Zelensky. Next name reaction, sorry, is your Hell-Bullard-Zelensky. What is Hell-Bullard-Zelensky? Why it is important? Let's see. Carboxylic acids having an alpha hydrogen are halogenated. What does mean halogenated? You are doing no change to we have discussed aldehyde, name reactions on aldehyde. We have discussed name reaction on ketone. Now we forward to name reactions on carboxylic acid. Very important, Hell-Bullard-Zelensky. Alpha position on treatment with chlorine bromine in the presence of small amount of red phosphorus to give alpha halocarboxylic acid. Reaction is known as Hell-Bullard-Zelensky. X2 means use Cl2, Br2. What you want to add? You want to add chlorine, then use Cl2. If you want to add bromine, then Br2. Red P, and many kind of phosphorus. Phosphorus based on structures, there are many different structures. There are white phosphorus, that is red phosphorus. Here red phosphorus is used. Water for hydrolysis. These are the reagents. What does it do? No change to COH group. Carboxylic group remain as it is. Sorry. Okay. What you want to add? Tell me. Chlorine, bromine. Let's add bromine. So I can't hear you. I can do what I want. Red P. Reagent. So one bromine will be introduced here instead of one hydrogen. COH group will remain as it is. Clear? What are the important notes? The reaction does not work with carboxylic acid lacking alpha hydrogen. Definitely, it will not react with Hell-Bullard-Zelensky, HBZ. No reaction. No reaction. No alpha hydrogen. It is not effective for fluorination or iodination at the alpha position. So why not? Fluorine is highly electronegative. It can't get, instead of adding up, they will like react and it will literally oxidize. So it will get oxidized. It will break the carbon bonds. It will form carboxylic acid. So iodine, why we can't add iodine by Hell-Bullard-Zelensky? Because huge size of iodine. Compared to fluorine, iodine, this is the size of iodine, or much greater than this. This is your fluorine. Suppose this is your fluorine. Suppose this is iodine. So how can you add that much bulky group to that middle? No, you can't. So these are the drawbacks, or you can say important thing to remember. As I said, only chlorine and bromine. Moving on. So these are the few examples you can see. I've made this for you. I've taken this reference. First one is your acetic acid. So alkaline Zelensky HV you can continuously add chlorine until all the hydrogen replaces it. Okay, see here. So, sorry. First step, we are adding, we are doing alveolar Zelensky. One chlorine is introduced at alpha position. Second step, you want to add chlorine. Left side, we are adding here again. Here you can see one hydrogen is left, so we can add one chlorine. In the third step, we are finally adding three chlorines here. So trichloroacetic acid is formed. So alveolar Zelensky, you can do it how many times you want until all the alpha hydrogens get finished, gets replaced. Then propionic acid, here we have bromine, you are adding bromine. So one bromine is introduced. The second step, two bromine is introduced. And see here, though no alpha hydrogen is present, so you can just add two bromine atoms. IPAC name alpha alpha dibromopropionic acid. So you can name in that way also. 1, 2, 3, 2, 2 dibromopropionic acid. This is your common name. Write down in your copy. Moving on, we have Hunziker reaction. What is Hunziker reaction? Let's see. How many slides are left? Let me see. What is Hunziker reaction? It's nothing but silver. It's your carboxylate ion that is reacted with silver salt. We call them silver salt, carboxylic ion that react with silver. Then silver salt of the carboxylic acid on treatment with bromine in the presence of CCl4. What are the reagents in Hunziker reaction? Br2, CCl4. These are the reagents. So another important thing, it had to be your silver salt of anything like COAG group must be present to your reacting species. So on treatment with alkyl halides having one carbon atom less than the parent acid. So COAG group will leave and one carbon less than the reacting species will be left. Like here, COAG. This is your silver salt. And if you do Hunziker reaction, see Hunziker reaction, you will just get benzene ring. One carbon less than the parent compound. So COAG will leave. COAG will leave, like CO2 gas will be formed as a byproduct and AG will settle down. AG will settle down. Oh, if you didn't understand, I can write the reaction here. CH3, first reaction is this, CH3COOAG plus Br2, proper in book language CCl4, they'll get CH3Br. This is their first reaction, plus CO2 plus AgB. Make a correction, not AgBr will be precipitate out. AgBr will precipitate. This is your Hunziker reaction. Next we have simple bromination, sulfonation, nitration. These are not necessarily name reactions, but I'm studying your organic chemistry, so many things will come up eventually when I discuss all these things. This is your basic bromination, FeBr, 3Br2, sulfonation, concentrate H2SO4, SO3H, SO3H group will be introduced in the benzene ring. So from here you can see carboxylic acid COH group is what directing? Meta directing. Similarly, deactivates the group. Is meta directing. Remember, lastly we are left with NH2. Let's see what NH2 is, whether it's OB directing or meta directing. Normal nitration, basic NO2 group is introduced. Moving on, we have come to the last chapter, that is your amines. Amines is a huge chapter, I guess. Amines contain reaction as well as theory. There are many exceptions, I guess. One, as far as I remember, there is one exception of 213, and I remember this in this way. This is your, I guess, pH3. This is your 1 degree amine. This is for the increasing of boiling point, I guess. This is your for 2 degree amines. So whatever. So this chapter contains reaction and theory and lot of exceptions, I know. Starting with ammonolysis. Ammonolysis is nothing but preparation of amine containing groups. Chemical reaction in which amine or amine react with a compound, typically alkyl benzyl halide, or an ester, causing replacement of leaving group. Cl will leave from CH3Cl, or CH3 NH2 group will be introduced. Similarly, that's what they are saying. Resulting in the formation of an amine, this reaction is analogous to hydrolysis, but ammonia replaces the role of water. So it keeps going on and on and on and on and on. Here, one example is given. You can see here, NH3 group. There are a total of 5 electrons in the outer shell. There is one lone pair. This lone pair attacks CH3. Suppose CH3Cl. Cl leaves. Chlorine doesn't leave. Chlorine gets attached to it and plus charge introduced to the methyl group like this. Why plus charge? Nitrogen can max to max bond 3, and they have provided 2 electrons, so it gets a plus charge. Sorry, I'll take a break. I was saying why plus charge nitrogen. Here it gives its free electron, lone pair electron, to CH3 group. It's vacancy or white it contains. So it attains a plus charge here. So Cl doesn't leave, it gets attached to this compound. So this is the product. This substituted ammonia salt. What's written? The free amine can be obtained from the ammonium salt on treated with a strong base. Just react it with a strong base. React it with strong base NaOH, your KOH, you will get the desired your. If you want 1 degree, then react it with once. Though this reaction is not feasible. Ammonolysis means, see, CH3Cl, this will keep adding on. Like here we can see, here one group is added, another group is added, until 3 degree, 2 degree, from 1 degree it gets converted to 2 degree, 2 degree to 3 degree, 3 degree to 4 degree, quaternary ammonium salt. So this reaction is actually not feasible. So if you want to stop the reaction, you just react with NaOH strong base to get your desired primary, secondary, tertiary amine, no problem. In this case, we are getting 1 degree. So here one reaction is given. As I have said, primary amine is obtained as a major product by taking large excess of ammonia. If you increase this amount, in like you give lots of ammonia, if you increase this amount, then only there is a chance that you will get like high yield of 1 degree amine here. This is from NCRT. Have you written all the things? Moving on, Gabriel thalamide synthesis. See, what we want to do, we want to prepare amines. Amines attached to methyl alkyl groups. So in Gabriel thalamide synthesis, we can only prepare 1 degree amine. Remember, 1 degree amine. What is Gabriel thalamide synthesis? Is used for preparation of primary amine. Sorry. Thalamide on treatment with ethanolic potassium hydroxide. This is your thalamide. already is attached to the. So it basically contains nitrogen attached to the ring. See, so you can just replace this and detach this. That's it. You will get your desired 1 degree amine. You replace this with any alkyl group, CH3, methyl, ethyl, propyl group, butyl group, anything you can have there. So produces corresponding primary amine. Aromatic primary amines like this, aniline. This can't be produced. Though it is 1 degree, this can't be produced by this process. They've already mentioned it because aryl halides do not undergo nucleophilic substitution reaction with the anion formed by the phthalimide. The anion which is formed here, it does not go under nucleophilic substitution with the aryl group, benzene ring. This group doesn't attach to it. So here is your reaction. First step, you are reacting with a strong base KOH to form your salt and N minus K plus. So after that you react with an alkyl halide, anything you want, CH3Br. You will get alkyl group attached to that nitrogen. Nitrogen makes total of 3 bonds. So here it is, halamide. And after that hydrolysis with alkali, you will get this group detached from itself within itself, and here peroxide ion is formed. Carboxylate ion salt is formed, double carboxylate ion, and you will get your 1 degree amine. Here I can show you one example. The many step, you can sum up the steps in one shot. Suppose I'm skipping this part. Okay, if you want me. See the structure carefully. Nitrogen forms a total of 3 bonds. If it makes 4 bond actions, then it attains a plus charge. If it forms 2 bond, then it will attains minus charge. And this K minus is not actually attached. There is a difference between writing NK and N minus K plus, because it means it indicates that this group will eventually leave and your alkyl group will get attached. So here, suppose CH3, CH2, Cl, suppose. So Cl will leave. See here. And after that, hydrolysis. Get your desired one degree amine. So basically here they have said ki this will not react. So they have said ki this is the benzene ring will not undergo electrophilic substitution reaction here. Okay, benzene will not get attached to N minus due to its structure. So here it is. See here, one example is given. So moving on, this is your Gabriel phthalimide synthesis, Hoffman bromide degradation reaction. Hoffman bromide is nothing but, in simple words, you have amine group, your NH2 group, you have your alkyl group here. Okay, you just want to attach this to, you want to remove this. Don't need this. To remove the carbonyl group, you have to remove the carbonyl group. So this is your Hoffman bromide degradation reaction. Hoffman developed a method of preparation of primary amines by treating an amide with bromine in an aqueous ethanolic solution of sodium hydroxide. In this degradation reaction, migration of alkyl aryl group takes place from carbonyl group to the amide of the amide to the nitrogen atom. See, as I've said, migration happens from this group to this group. This amine so formed contains one carbon less than that of present in the amine. Definitely, if it contains 3, here it was your double bond O, total it was 4, then this group is vanishing, you are remain with 3 only. The one carbon less than the compound which you have taken. So here is one example. So bromine, NaOH, these are your reagent in Hoffman bromamide degradation, HBD. Happy birthday. So what are the reagents? Bromine, NaOH. If not, if necessary, then write 4 moles, okay? Then you will get your amine, desired amine. It acts for both aryl compounds as well as alkyl compounds. That is the plus point of Hoffman bromide degradation. So that one advantage you got out of Gabriel-Salamide synthesis. It acts for both. Just take amide for any aryl compounds or alkyl compounds and go for Hoffman bromide degradation to get your desired primary, secondary, tertiary, whatever amines you want. The amine so form contains one carbon less. So this is one reaction. Yes, you can see here. If it's not visible, let me zoom it for you. Here are 3 examples. You can write it in your copy. Also, students, if you have any doubt regarding this whole presentation, whole lecture, you can ask it in the comment section. If you have any doubt, if you have missed anything, so you can watch according to your will. If you have confidence that you know this reaction, you know very well, then skip it. Don't need to waste your time, whether it's 10 minutes, 15 minutes, whatever. I've tried to break everything for you. I've tried to make you understand what reagents are actually doing in a reaction, or if you take aldol condensation or the exception in your Williamson ether synthesis. I've tried to include all those theory part in this lecture as well. So moving on, diazotization. I guess this will be the last part. Diazotization is very important topic. Diazotization, after that you are left with Sandmeyer's reaction, Getterman reaction. Let's see what is diazotization reaction. Aromatic primary amines react with nitrous acid prepared in situation from NaNO2 mineral acid, NaNO2 HCl. These are the reagent in diazotization at low temperature. Very important to mention the temperature, that is your 0 to I guess 5 degree Celsius. So diazonium salt, the conversion of primary aromatic amines to diazonium salt is known as diazotization. This is your benzene ring, aniline. This is your basic aniline. You are giving all this NaNO2 HCl temperature. This you are left with this. We call it diazonium salt. So after that, diazonium salt is used to make a wide variety of compounds. Wide variety. You can make a lot of. This thing is very important while doing. This thing is very important while doing your conversion reaction, your multi-step reaction. I know you have doubt, it's difficult to do multi-step conversion, to learn all the name reaction or all the extra electrophilic substitution, nucleophilic substitution, but you have to know this. So this helps in wide range of conversion. Okay, so diazotization used in multi-step conversions. Moving on, Senmay reaction. Senmay reaction is nothing but in this reaction, chlorine, bromine, cyanide can also be introduced. What you want to add? If you want to add chlorine to your benzene ring, if you want to add bromine to your benzene ring, if you want to add cyanide to your benzene ring, in the benzene ring by treating with diazonium salt with corresponding halogen acid in the presence of copper. what does it do? You just need copper, your halogen acid. So halogen acid, if you want to add C chlorine, then your HCl, then HBr, hydrogen bromide, HCN. Sorry, here it is written KCN. Potassium cyanide, HCN, you can also react with HCN. And copper is mandatory. Copper is mandatory in Senmay reaction. Copper 1 ion. So here it is. So you can see Cu2Cl2 gives copper 1, Cu2Br2 gives copper 1, CuCN gives copper 1. It's very understandable. So this is your product. This is a nitrogen gas is released. If we had to draw this, I can draw it for you. Copper 1, your HCl, your HBr, your KCN, same copper 1, copper 1. So this is for you. Not copper iodide, copper 1. 1 ion. So moving on, what do we have now here? Getterman reaction, very different from Senmay reaction. Let's discuss. In this reaction, chlorine, same, we want to add same thing, chlorine, bromine. Senmay gave his reaction, Getterman gave his. Or cyanide can also be introduced in the benzene ring by treating with diazonium salt with corresponding halogen acid in the presence of copper powder. Just the copper powder. In that case, Senmay used your Cu2Br2, your Cu2Cl2. This is your Senmay, CuCN, and here you are just using copper powder. That's the only difference. Also, like in the first part we have discussed, right? You want to add chlorine, bromine add kar diya, फिर से. So what is left? Chlorine is left, iodine is left. You want to add fluorine, iodine to your benzene ring. If you go for fluorine, fluorine needs Boltzmann reaction. You have one, your fluoroboric acid, and your iodine. If you want to add iodine, just react with Ki and just react diazonium salt. With Ki, sorry. We'll get this product. We'll get iodobenzene. And for fluorine, we'll see later on, there is Boltzmann reaction. Getterman reaction, the yield in Senmay reaction is found to be better than Getterman reaction. Though both you have to learn the both thing. You have to like know the Senmay reaction, Getterman reaction as well. But yield is better in Senmay reaction. Moving on, there is deamination. Deamination, I'll not see here. I'll just tell you here. Very short part. So you want to add chlorine, fluorine, your iodine to your benzene ring. So what in case you just want to get your benzene ring back from your diazonium salt? So you basically have to react it with mild acid, that is your hypophosphorus acid, your H3PO2 or your C2H5OH ethanol. Just react either of these reagents, you will get your benzene ring back, okay, from diazonium salt. Okay, we just want to add hydrogen. So this is your reaction. So H3PO2 is, you can give C2H5OH, mild acid. So here you will get hydrogen attached to it. Whether you want to write or not, it's up to you. You can just get benzene ring back. So these are the byproduct. So hypophosphorus acid, that is your H3PO2, is oxidized to your H3PO3, and your C2H5OH ethanol is converted to your ethanol, okay, aldehyde. Here it is oxidized, here it is oxidized, here as their mild oxidizing agent. That is your language. So what do you have at last? The coupling reaction. Colored compounds are formed when you react diazonium salt with phenol. It just this reaction. With phenol. This is your coupling. Your coupling reaction. It has a characteristic color you can see here. Example of electrophilic substitution reaction. You can pause the video and see the theory. See here. The N2 plus Cl minus. So those who have doubt ki how does N2 plus Cs minus Cl minus exist, here is the structure. Nitrogen makes here 4 bond, that's why it gets plus charge, and NCl is the structure. So they produce a color compounds. They are used to. This is the color of orange. This is orange. Here orange, and this is yellow. Yellow dye. So now you can remember, because visual learning is much more easy. This is the color of yellow. So there is aniline, it reacts with aniline, it forms this yellow compound, and all it forms orange compound. Moving on, as I said, you want to add what? Fluorine to your benzene ring. Just go for Boltzmann reaction. You react with fluoroboric acid, HbF4 is your reagent. Then what is? Let me draw this benzene ring properly for you. Like I am doing it very casually. Sorry, students, you have to do it like this. Here I am doing it again casually. My sir used to tell me ki if you are doing it casually, then good, and it means you are studying. If you benzene ring looks like this, okay, so you are drawing it for the first time, definitely. You're not practicing even circle. If you're doing it the circle like this, you're doing it for first time. You are not practicing any organic reactions. You are not studying organic chemistry. If you're doing it like this, if your benzene ring converts to this, Now I know that you are practicing organic chemistry, you are doing conversion, you are doing NH1, you are doing everything. Whatever. Just want to share a small incident with you. This is PM4 and benzene ring. F is introduced. Actually, there is a complex form N2 plus GF4 minus, but you don't have to write this thing necessarily. Just write this directly. This is ball schema. Next, next, I guess this is the last part of our video. Though these are not under any organic normal step reactions or multi-step reactions, but I have tried to put all the conversion in one slide. So one present one slide. So here you have this. Want me to zoom it? Here it is. I guess you understand it. So they are same benzene ring. This is your enamine. You're doing diazotization, diazotization. After that, you are getting your N2 plus Cl minus. So see here, so it is not basically here, I guess, H2O1. So it was not a name reaction, but I've tried to keep all the reactions in one step so you can like have a look. So if you want to convert this to phenol, just react with H2O warm water. This you want to add hydrogen, go for H3PO2. What is this? Tell me. Whether it's Senmer or Getterman. This is Senmer. This is Getterman. People make a lot of confusion. Again, Cu2Br2 Senmer. This is Getterman. Cu HBr. This was your Senmer. Cu2Br. I'm not writing here, it will be confusion. This was your Senmer, this is your Getterman, this is your Senmer, this is your Getterman. Again, this is your Senmer. This is your what? This is your, also your Senmer, potassium iodide. This is your ball schema. This is your also ball schema has another part, that is if you want to add NO2 group, you want to produce nitrobenzene. So you can just react it with NaNO2 as well, along with HBF. You want to add SH group, iosulfide, then you can go for KSH. You want to do coupling, there this is for coupling. I guess this is the end of your video. Wait 5 minutes. Lastly, I have one reaction to show you. It's very important. It's used to distinguish all those your aldehyde, ketone, whatever you have, your aromatic compounds. It's important. It's haloform test. Wait, I'm coming back. So lastly, we have haloform test. Okay. I think I broke my voice shouting. So hopefully you understand well all those were all the name reactions that I have taught you. So it will help you a lot. Also, if you don't know any organic reactions, any name reactions, I guess this video is perfect for you. You can do both revision, both exercise, and both learn from this video as well as how I have done the aldol condensation, Gabriel phthalimide synthesis, and different Hoffman bromide degradation, everything. Ammonolysis, you can learn eventually. So, this is not just your one shot doing name reaction, it's your one shot in organic chemistry. So though organic chemistry is very huge, so okay, moving on. Also, if you have any doubt until this, you can like ask it in the comment section, or you can go through the contact number given to you direct to with Alpha. If you have any confusion, anything to ask, so you can just contact. I guess the contact number or the details have been shared to your comment section or in the later part of this video. So lastly, we have a hello form test. I find it very important. People, it's for those question which ask difference between compounds. Many students skip this part. Hello form mainly consists chloroform. Like if you react with, if you are using this as a reagent or this, both means the same thing. If you are using this, you don't need to write this. If you are writing this, don't need to write this. This is your chloroform reagent. Another one is iodoform. Characteristic yellow color. Yellow color test. Heavily used in aldehyde, distinguishing aldehyde ketones and different compounds. Here the reagent is iodine and sodium hydroxide, as well as you can write NaOY. It's up to you what you want to write. So under heliform test you have to. This is the product in chloroform. This is the product in iodoform. Okay, you may ask where is the reaction. Well, let me show you. Suppose you want to distinguish this. This one compound, this, let me draw it clearly for you. Okay. Let me see. Let me show you. So, hello form test. Hello form test is done when you have free methyl group. What? Free methyl group. Okay. It undergoes only when you have a free methyl group. That is your CH3. I guess you know methyl CH3. So do you have here free methyl group? Is a ketone. You want to suppose distinguish between this and this and this and this. Okay. Suppose HCHO. You are to ask difference between this and this. So how do you do? Does it contain free methyl group? Yes, it does. It will give haloform test. Now you want to do chloroform or iodoform? Go for iodoform. Learn what is the product. Definitely you are doing iodoform, so one methyl group will react and CHI3 will be produced. Another will remain as it is because it just react with 1 mole. This will be the product. Okay, this is a yellow color. So if you want to distinguish this, does it contain any methyl group, free methyl group? No, it does not contain. So it will not give no iodoform test. No yellow color compounds. So this is the yellow is the color of CHI3. So does it contain Methyl group, free methyl group, yes, it does contain free methyl group. So it will give, you have done iodoform, let's do chloroform. Of course, characteristic is the smell, chloroform. What will be the product? C double bond O, ONA. Methyl group will come out. Simple. Does it contain a free methyl group? Does it contain a free methyl group? Yes, it contains. But there is no reaction. Why there is no reaction? Because the free methyl group have to be attached to this carbonyl group. This carbonyl group. Does it attach to the carbonyl group? It is attached, but there is a different group in between them. So this will not give any haloform iodoform test. Okay. There is free methyl group, but not bonded to carbonyl. CO bond. This will not give. Whether it will give reaction? Does it contain any free methyl group? Does it contain any free methyl group? Yes, it does contain free methyl, not directly to the carbonyl atom. Carbonyl carbon, sorry. So it will not give any test. No iodoform, no haloform. No test. No reaction. I guess all this is clear for you. This was the last part. I've kept it for last, the haloform test. So thank you, students, for your cooperation and being with me for last, I don't know, 2 hours or something. Thank you for being with me. I hope you understood each and everything clearly. There is nothing to mog up anything. Just take time, understand, okay, and just revise whatever you have. Okay, thank you. And if you have any doubt, any question regarding this, you can ask it in the comment section. Okay, everything will be provided to you. Or if you want to contact with Alpha, then I guess contact details, everything is shared here. So if you want any lecture, like if you enjoyed this video, if you want any lecture regarding organic chemistry or anything regarding chemistry, you can ask it in the comment section. So we can come up for you with different videos, different lectures like this. If you want to cover this chapter in one shot, that chapter in one shot, if you want to cover this topic in one shot, so you can ask it in the comment section, anything you want. So it's lovely experience to teach you all. So I find it chemistry very interesting. So keep studying and keep revising. Revising is must. And also I guess this video is helpful to those who will be appearing for boards, those who will be appearing from entrance. There is a lot of examples I've give you. Also, that's it for today. Thank you. Tata, bye bye.